So thanks, Henry. So this is the Pluto system orbiter and Kuiper belt explorer that we've called Persephone. And this is, as the name sounds, a mission concept that would go back to the Pluto system following New Horizons' successful exploration of it, and really try and explore the Kuiper belt as well. We're nominally trying to add 2 extra Kuiper belt targets into the exploration. So before I go on, I just want to give a quick shout out to our team. We've been partnered with APL, and that's been really successful. So a big thanks to Stuart Robbins, who is my deputy and really led the team when I was out on maternity leave at the beginning of this process. So thank you to Stuart, and Carl Howett, which is the APL lead, and he's done a great job of herding the cats, especially at this very disruptive time. And so thank you to him and the full science team and the APL support team. Really, this is, I'm just presenting the work that we've all done together, and I just really appreciate everyone's time and efforts. So thank you. All right, now let's get on with it. So our mission is to explore the Pluto system and Kuiper belt, and we have 3 big science questions that we're trying to address. So what are the internal structures of Pluto and Charon? I'm going to talk a little bit about why we think that's important and what the potential astrobiology implications of that are, but what the science drivers are there. How the surface and atmospheres in the Pluto system have evolved. We learned a lot about the Pluto, particularly the atmosphere. That was really exciting, I think, from New Horizons, but looking at how they were changed. And then the wider KBO population. So how has that evolved, and what do we know about it? Really, we've only seen one classical KBO, which was Arakoth, that New Horizons flew past in 2019. And of course, the Pluto system, New Horizons flew by years before that. So this is a population that we really don't know a lot about at the sort of resolved level. And Pluto is a long way away. A lot of the work that we did was looking at the trajectories, how we get there. Most of the instrumentation is already been used. It's high TRL. So a lot of our processing and lots of our time was spent looking at how to get there and how to operate there. As you'll come to see, we need 5 RTGs, which we know is a big number. We iterated on this a lot. There's a trade between the number of RTGs you take and the amount of power it can provide, of course, but each RTG is heavy. And so that delays your arrival time. So there's this sort of trade that we ran between. We were trying to get it down to 3. We ended up really deciding we needed 5. And then finally, we have 3 kind of phases. The first is the cruise to Pluto, and we've got a KBO flyby as part of that cruise. So really our KBO tour starts before we get to the Pluto system, which is different to New Horizons. 3.1 Earth year tour of the Pluto system, so looking at Pluto and Charon and the small satellites of the Pluto system, and then an extended mission to explore a post-Pluto KBO. And I include that here because in order to do an extended mission, we need to carry extra xenon, and so that affects the operations of our nominal cruise, our nominal mission. And so we have to kind of consider that trade when we're considering our nominal mission. Okay, so a quick glance through the science goals. I hope I don't need to convince you that Pluto and Charon are quite enigmatic and interesting targets. One of the big drivers is to understand the internal structure of Pluto and Charon. So particularly, is there a subsurface ocean on Pluto? Is Pluto an ocean world? This could be reworded as. The driver for this was some of the New Horizons data that showed Sputnik Planitia, which is part of that heart-shaped region that New Horizons saw. Is topographic low, but it's a positive gravity. And so Francis Nimmo put forward a paper in 2016 outlining that maybe this was due to a subsurface ocean that this graphic kind of illustrates. It's coming closer to the surface and provides that positive anomaly, even though it's a topographic low. There's also some really interesting features on Charon that point to it having a subsurface ocean in the past. We wanted to understand whether they're differentiated and whether there's a magnetic field for either of these targets. The level 2 questions are really kind of get at the surface and atmospheres of the Pluto system. So New Horizons showed how exciting Pluto's surface is, and Charon, of course, but the atmosphere of Pluto is just phenomenal, as the bottom figures show here, lots of haze structure. And so we want to better understand the relative ages and processes that are going on these targets, but also looking at the volatiles and the chemical composition of these targets. So we wanted to do in situ measurements, for example, with the mass spectrometer, looking at what the composition of these targets are, and then looking at the escape rates of heavy and light ion species. The final sub-level science goal is really looking at the wider KBO population. So we do include in here the small satellites of Pluto and Charon, but really we want to really we're looking at the implication is about how KBO systems can evolve. We want to better understand the surface properties, their composition, volatiles, and any atmospheres that do exist. So we, as the bottom right-hand figure shows Arakoth, which is the only cold classical Kuiper object that we've ever encountered. It's very different to the Pluto system, objects in the Pluto system, as you can see here. But really, we want to better understand the wider population of KBOs, and do they really support some of the current streaming instability models, and really kind of looking at how are they formed, whether our current models are accurate. So most of the rest of this, we have some level 2 science objectives. I forgot about those. So Pluto's internal heat budget, that kind of gets back to this idea of what's going on in Pluto's interior. And then the structure of magnetic fields. New Horizons did, of course, have particle and fields instruments, but by orbiting the system, we can better understand, for example, is there a Pluto pause? And we'll be out in the deep solar system, so we are carrying different instrumentation suites. So one of the other questions we wanted to look at was how pickup ions affect shocks throughout the heliosphere and around solar system objects. Okay, so this is our payload. As I said before, they're all really high TRL. All of them have flown or will be flown soon. So we have 11 nominal instruments. So the first is the Panchromatic and color high resolution imager, and we've modeled that on the Europa Clipper ICE NAC. And this is going to enable us to, this is going to be our OpNav camera, but it's also going to enable us to get phenomenally high resolution images of the targets that we fly by and encounter. A low light camera. This was really important to us because the subsolar point when we're likely to encounter Pluto was quite similar to New Horizons. So the parts of the terrain that were in winter darkness will continue to be in winter darkness, but we want to understand those regions too. So a low light camera, which is modeled after Europa Clipper's ICE WAC, will enable us to do that, especially on Charon when it's facing away from Pluto, because that terrain is very poorly lit, but also, of course, in the winter regions on both targets. A UV spectrometer akin to New Horizons ALICE, when we're in orbit in the Pluto system, that's going to enable us to get very detailed information about the atmospheric structure of Pluto. A near IR spectrometer, this is the Lucy version of LEISA. So LEISA also flew on New Horizons as part of the RAL suite. The Lucy version has an extended wavelength range that we thought was important to better understand the organics on Pluto. And so we'll be flying that, or we're proposing that should be flown. A thermal IR instrument. New Horizons did not carry anything in the thermal IR. Of course, we'll be able to look in the dark regions in the thermal IR, and this will enable us to get a better idea of what the heat flow is and what the structure of the surface is in the Pluto system. So we're modeling that after THEMIS on Mars Odyssey. An RF spectrometer, of course, to investigate the atmosphere of Pluto, but also to communicate with the Earth. That's the same as the New Horizons REX instrument. A mass spec modeled after mass specs on Europa Clipper. So an in situ measurement that will enable us to understand the atmosphere, particularly of Pluto. An altimeter modeled after Messenger MLA. So an altimeter really gives us an idea of what the relief is across Pluto and the other targets. As we've shown, as I was talking about before, understanding that relief really gives us information on what the subsurface must be doing to support that relief. And so this is going to be really key to understanding what the topography is on these targets. An ice penetrating radar, which is terribly exciting to see not just the surface, but below the surface, particularly on Sputnik Planitia. This would really give us an insight into how those convection cells are working. So modeled after Mars Express MARSIS. And then a 3-axis plug gate magnetometer, basically the MAG on IMAP, and a plasma solar wind ions and electrons, also modeled after the IMAP CODIS low instrument. And so this suite we think would absolutely revolutionize our understanding of the Pluto system and other KBOs. It's going to do phenomenal science. This is our nominal design. So you can see at the bottom, there's our RTGs. One, of course, is hidden behind the huge xenon tank required to for the electric propulsion system to get to Pluto, but also to move around the Pluto system. We have a remote imaging deck, and so that includes all of our instrumentations, as you can see here. And then we have two structures. So we have a mag boom and a nice penetrating radar antenna. And then, of course, the communication dish with the Earth. This is there's a meter scale bar put at the bottom. This is a huge satellite. So, you know, kind of think more Cassini than New Horizons. And just for comparison, this is shown to scale. So our proposed spacecraft versus New Horizons. And so New Horizons was about the size of a grand piano, about 2 meters, almost cubed, whereas Persephone is much bigger than that, as this slide shows. Okay, one of the things I already kind of alluded to, the complications with this was just getting to the Pluto system. So this plot on the right-hand side shows you launch date on the x-axis and time of flight on the y-axis, with the colors being the arrival speed into the Pluto system. So obviously slower arrival speeds are better if you want to get in and orbit a system. And so what this shows is up until about 2032, Jupiter is in phase. You can get there at about 18 years with this phasing. But after about 2033, Jupiter is out of phase. It can't help you get to the Pluto system. And the cost of that is almost a decade. So it almost costs you about an extra 10 to 15 years just to get to the Pluto system if you launch after about 2032. So one of the other questions we wanted to look at was how pick-up arms. Can somebody mute? Thank you. Okay, I was hearing myself. That was weird. This was a big part of our trade space. And so, of course, that again, these numbers wiggle a little bit depending on what your delivered mass is. But fundamentally, it means in order to get to the Pluto system in under 20 years, you need to launch before 2032. So this is our nominal trajectory. As I said before, we launched on an SLS Block 2 with a Centaur kick stage. We're using an EP system, and we have 5 RTGs. In order to kind of derive this tour, we have a nominal launch date in 2031. So when Jupiter is still in phase. We then encounter Jupiter a year later. We have our first KBO encounter, and I'll talk a little bit about that and the trade space around that on Christmas Day, 2049. So it's going to destroy our holiday plans in a decade or two. And then a Pluto rendezvous in 2058. So this gives us a time of flight to the Pluto system in about 27 years. This is a long time of flight. We have a deviation, which is costing us an extra year in order to do a pre-Pluto KBO encounter. And the reason that this takes longer than the shortest possible time, which I showed on the other side, is that our delivered mass needs to be high. It's about 2,600 kilos, so just shy of 3,000 kilos, which it's a big spacecraft. On the bottom left-hand plot, this is the XZ plane, and you can see just how far Pluto is, which is sort of the blue circle around number 4, out of the ecliptic. And so this is a challenge for a number of reasons. One, of course, it adds distance that you need to travel, but also it means that Pluto is away from the main body of the Kuiper belt, which it's a lot more dense in the ecliptic. And so this makes exploring other Kuiper belt objects a little bit more difficult. And we did some statistical work at looking at what our options might be. Okay, so what you're seeing here is a model, the output of a model that J.J. Cavallard put together. So thanks to him and John Spencer and Simon Porter for really working this. The red line in the model is our trajectory. And the green little dots are statistical KBOs that we would be able to encounter from our nominal trajectory with some deviation. The colors indicate the closest approach dates. And so we had a trade-off to make here. You know, how much deviation did we want to do in our nominal trajectory in order to investigate a KBO before we encountered Pluto? And you can see on the top right-hand plot, a nice plot that graph that Fazil Sadiq at APL put together for us. He's done phenomenal work looking at our trajectory, and it basically shows the additional time you need to add to your cruise time to Pluto in order to deviate. And so we selected a deviation of about 1 AU was acceptable in our nominal cruise time, which gave us a penalty of about a year. And this was done because the statistical work showed that if we deviated from about 0.2 AU, we got to see something that was about Arakoth's size, so the order of magnitude about 30 kilometers. But we needed a bigger than about half an AU to visit a larger target. And we decided that an extra year, if it's going to take you over 25 years to get to a target, to maybe visit something that's 100 kilometers instead, was worth that extra time. So the bottom right hand plot now shows exactly the nominal trajectory and the deviation that was included in our trajectory to do a pre-Pluto KBO. Okay, so now I'm going to describe the Pluto tour. This was a really interesting part of our sort of trade space and how best to investigate Pluto and Charon and the small satellites. We have a very small delta V budget, but of course we want to do phenomenal science. We've gone all that way. You want to be able to make sure that you can see the targets and do the science you want to do. So previous study have really fought Charon. It's a binary system, and Charon really does complicate things. But Fazal took a somewhat innovative approach to really just use Charon instead, and came up with these repeatable periodic orbits that enable us to really investigate the Pluto-Charon system using a very low delta V budget. Because it's the tours themselves operate in the Pluto-Charon fixed rotation frame. So that gives us repeated ground tracks, which are really interesting because they repeat on the surface, but the time of day on the surface where you encounter the surface changes. And so that enables us to build up local time coverage, which is really important in order to achieve our notional level 1 science objectives. So we chose, the periodic orbits themselves fell into 2 categories. So high latitude coverage, which we really wanted to build up global coverage. This was important for understanding the gravity, but also just in terms of understanding both of these worlds, both Pluto and Charon. But we also needed low altitude coverage. The in situ measurements, of course, need to be, especially those like the mass specs, for example, want to be able to directly sample the atmosphere. And in order to do that, we need to be at low altitudes. We're going to use the EP system to move between them. And any future study could decide on many of these orbits. We selected 4, 2 of which gave us high latitude coverage, 2 of which gave us low altitude and low latitude coverage, which we felt was a good trade in order to achieve our science objectives, but not to spend too much time transitioning between the orbits. So this is a description of all 4 of our science orbits. They've all got the same layout, so I'm just going to take a minute to describe what you're seeing because it's a somewhat confusing plot. On the top left-hand side, that shows the Pluto system if you're looking at it from above. So the black dot in the middle is Pluto, the black dot to the right-hand side is Charon, the 4 pink dots are the Lagrangian points. The dotted lines indicate the location, the orbits of the small satellites, and the blue line is 1 revolution of this science orbit. So you can see that it's not an orbit in our traditional sense. We get multiple encounters or periapses with Pluto and with Charon. If you look at the bottom left-hand plot, that shows the same thing, but in the XYZ plane. So what you might think originally is this orbit gives you really nice coverage of the small satellites. We certainly get out to those distances. But if you look in the XYZ plot, you can see that when we encounter those distances, we're a long way out of that plane. And so the distances actually are still quite large. If you look on the right-hand side now, these are our ground tracks. So they're only shown at altitudes at less than 40,000 kilometers. But you can see that we get really nice, for example, on Pluto, high latitude coverage. The dots indicate the location at the periaps, and the color indicates the altitude at that periaps. So this one we selected because it gave us really nice high and low latitude coverage of Pluto. It also gives us very nice anti-Pluto coverage of Charon, sort of equatorial and mid latitudes. So this next one is the other high latitude coverage observation set of orbits that we chose. So this one now, of course, gives us really nice high latitude coverage of Charon, but we get really nice Charon facing and anti-Charon facing coverage of Pluto too. All right, so this one is the first of our low latitude and low altitude coverages for Pluto. You can see that in the top left-hand plot, we do spend a lot of time sort of very close to Pluto, which is going to be really good for our in situ measurements. We also have really nice ground tracks over Sputnik Planitia, which is a big region of interest to understand what's going on in that very active region. And the coverage on Charon is very complementary to the coverage that we got in the other orbits. And then finally, this is the fourth low latitude tour. It's very, very close to the equator now. But you can see in the bottom left-hand plot that we really do stay in the Pluto-Charon plane. And this will give us nice coverage of the small satellites as well. You can see that we cross those, their orbits multiple times and kind of get out towards their orbital distance multiple times. So just to kind of walk through what we thought a possible tour might look like, the right-hand plot is that 3D plot showing you what the tour looks like. And this is our full tour when you put it all together. So it's 3.1 years or just over 1,100 days, Earth days. So we start off in orbit 1 science mode, and we do this one orbit 4 times. So the nomenclature we're using is an orbit, just describes what I showed before. So one orbit has multiple periapses, but then you can do it a number of times. And this is to build up local time coverage. And so we plan on doing this 4 times. This orbit lasts 46 days. So you end up spending about 180 odd days. In order to then move between orbit 1 and orbit 2, you need to be in the optimal part of orbit 1, and then you do your transfer, and that puts you in a part of orbit 2, but maybe not at the sort of nominal beginning of orbit 2. And so that's what's described by the next step, which is this departure phasing, so moving to the correct part of orbit 1 to leave it, and that'll take a day. We then have this transfer time between orbits, and this is, during this time, we can't do any science. All of the power goes to the EP system. So we'll be able to have some communications, but largely this won't be science time. But then we have another 28 days where we're sort of entering into orbit 2, but we haven't quite hit the beginning of the orbit. And so we have 28 days where we'll be taking science before we sort of hit the beginning of that second orbit. So that's what's shown here. This orbit lasts 29 days, and we aim to do it 3 times. So it takes us almost 500 days into the mission. We then leave orbit 2, and we sort of work our way into these low altitude orbits. So it takes about 30 days in order to make that transfer. And we get about half of an orbit of orbit 3 just from phasing when we arrive. So of course, we'll be doing science in that time. And then we just do 1 revolution of orbit 3. This is a really long orbit, as you can see here. It's over 150 days. And during that time, we'll be building up coverage of the small satellites and low latitude features on Pluto and Charon. And then we move between orbit 3 and 4. This is our final transfer. And we end up in orbit 4, which we do 3 times. And this enables us to get really nice coverage of the small satellites too. Now, the next few slides show the coverage that you would get just nominally using these instrumentations. And all we've done here is we've taken our fields of view and we've looked at what you'd get if you just look nadir pointed, and then 10 degrees away from nadir on one side and then 10% on the other. So we haven't really optimized to get mosaicing. This is just a first cut of the type of coverage you could get with kind of a minimal change to the spacecraft pointing. And this is our NAT coverage. So it's just a reminder, that's panchromatic and color imaging. And the scale bar here is in meters per pixel, and it maxes out at about 100 meters per pixel. So you can see most of it's taken at better than about 50 to 60 meters per pixel, or most of it's taken at about 40. And to put that into context, I wanted to play this movie for you. This is the highest resolution, if the movie plays. There we go. This is showing you the highest resolution images that we got of Pluto from New Horizons. So that is a single strip, And I sped it up a little bit because I didn't want to spend too much time showing you these results. But this is about a factor of 2 worse than we will get with flying the NAC across the whole of Pluto. So not just for a single strip, but for the whole of Pluto and Charon, or nearly Charon too. And you can see the phenomenal results that you would get. You can really resolve the little pits on Sputnik Phoenicia, what you're looking at now. And as we move towards the limb, the rough terrain that is around the edge of Sputnik Phoenicia, so the mountains and possible cryovolcanoes at the edge of the Phoenicias. This is showing you the same thing in case the movie didn't work. So like I said, again, we'd get about a factor of 2 better than this, but over the whole target. One of the things that we've been concerned about is the emission and incident angles that we would get. We want to make sure that we can get good photometry across all the targets. So we've done a first cut at looking at those. And a huge shout out to the Cybox team at APL for helping us make these plots. They've been really useful in making sure that we can achieve our level 1 science with our current plan. So I don't want to get into these, but it's just to show we're thinking about that, and we think we've got a good plan in order to get the coverage that we need so we can do that. This is the coverage that we would get with the WAC. So as a reminder, the WAC is going to be our low light camera. So we're focusing on the dark terrain on Pluto, so the region New Horizons didn't see. The resolution is about an order of magnitude worse than we get with the NAC, but would still absolutely be phenomenal. This is not terrain that we've imaged at all, really. It's been very hard to image in the past. This is the coverage that we would get with LEISA. So LEISAs are near IR spectrometer. Again, you can see there's some holes in our coverage. We haven't optimized this at all. Like I said, this is just for nadir and then just slightly off nadir pointing. But at worst, it would be 1 kilometer per pixel, which would really enable us to have a good understanding of the type of compositions we're seeing across Pluto. And of course, we can only do this in the sunlit hemisphere, which is why you're not seeing any footprints in the lower third of the Pluto map. This is our coverage with THEMIS, so our thermal instrument. It's about 10 kilometers per pixel. 10 kilometers per pixel. We can image all of Pluto at. We can, of course, do the dark regions on Pluto in the thermal, and this would give us a great idea of what the structure of the Pluto surface is, but also give us a handle on somewhat of the heat flow. And of course, we can use this to look for hotspots should they exist. One of the things we've been thinking about with the thermal instrument is the local time coverage that we would get of Pluto. I don't really want to get into that, but just to show that this is something that we're considering. We want to make sure we get day and nighttime coverage of across Pluto so that we can get a good handle on what the surface properties may be. This plot shows the ground speed for the encounters. So New Horizons flew past Pluto at a phenomenal 14 kilometers per second. This color bar shows what the ground speeds are of our encounters, and it tops out at 1 kilometer per second. So almost an order of magnitude slower, well, over an order of magnitude slower than New Horizons. So this would really does enable us to get phenomenal science. We have a lot more time on these encounters. We've been looking at the occultation opportunities. So this shows the distance to the limb and the location, so the footprint of where we'd be looking for Earth and solar occultations, which are going to be important for ALICE and other in situ measurements. And also stellar occultations. This shows just what we'd get with 10 UV bright stars. Of course, there are hundreds of UV bright stars, but just by looking at the 10 of them, it shows that we get good local time and good coverage over the surface. And then finally, not to miss Charon out, we haven't optimized for Charon, but this just shows kind of what you would get with the NAC. Roughly speaking, it's better than 100 meters per pixel. So really, again, you know, that strip that I showed you for New Horizons on Pluto was 80 meters per pixel. And so this is, most of this is going to be at 100 meters per pixel. So it's sort of that order of magnitude. And the understanding we'd get from Charon would just be phenomenal too. This is a bit of an eye chart. I don't want to go into it. I just wanted to show that we've been thinking about data volume. Mark Perry at APL has been thinking about this a lot. So thanks to him for this work. And we fit into the box using the decadal guidelines. We're going to be taking a lot of data, but we also have a lot of time to downlink that data. And so if we assume 28 kilobits per second over 2 years with 7 passes a week, 8 hours a day, that gives us a budget of 587,000 megabits. And we can all get all level 1 science under that at 584,000 megabits. We still need to do some work maybe on Charon and the small sats. Right now they've just got an allocation, but at least a first order we can fit in the box. I don't want to spend too much time talking about extended missions, but I did just want to talk a little bit about it, because in order to enable an extended mission, we have to take extra xenon with us, which increases our cruise time. And so to have an extended mission, it has an effect on the nominal mission. This plot shows the post-Pluto distance versus how long it takes you to get to those distances for different amounts of xenon that you're carrying. And so we talked a little bit about this using some more statistical work that JJ and John and Spencer and Simon Porter led. It looked like if we did if we went 1 AU, we got about a 40 kilometer possible KBO. 3 AUs brought us something around 70 kilometers. And so we thought the sweet spot between delaying the nominal mission arrival time, but also enabling us to do future KBOs was about 250 kilos. Of course, future PIs might decide on a different trade, but that's where we kind of landed to enable us to explore something, a KBO that was potentially exciting, but not to delay the nominal mission too much. With that, Brian Holler had a look and see what known KBOs we could get to for that sort of xenon cost. Depends on how long you want to wait. If you're happy to wait up to 20 years post-Pluto, then you can get to something pretty exciting, something of sort of order of magnitude of 600 kilometers. If you'd rather do that faster, a known target might be 2013 JR65, which is we could reach in up to about 13 years. The statistical work indicated that we could reach 150 kilometer sized object in about 8 years. So there's a ways at which you can kind of come up what a post-Pluto KBO tour might look like. So to summarize our trajectory, the interplanetary cruise time is about 27 years. It includes a pre-Pluto KBO flyby. And this would have to really be kickstarted, or this tour would have to begin before 2032, the end of that phasing. So a 2031, 2032 kind of launch window. We have a 3.1 years for a planned tour where we survey Pluto and Charon using periodic orbits and other small moons, and we're going to keep our EP system to do that. And housekeeping would be done with a small amount of hydrazine, which I haven't actually mentioned. So, and then a post-Pluto KBO. We're going to reserve 250 kilos for that, where we can get to something sort of 100 to 600 kilometer size object within sort of the 8 to 20 year range, depending on what you assume. This is a bit of an eye chart, so I apologize, but I kind of want to make the point that with those launch windows, that's really driving when you'd need to start. So if you assume that you want to hit the first launch window, so you've got 2 backup launch windows in, say, 2030, phase A needs to start in 2023. Oh, sorry, 2021, so next year. But you do have some wiggle room there with an extra couple of years. And then, of course, if you're willing to have a longer cruise time, that could be extended either still. And this is in a pretty aggressive schedule. But I think that's one of the important things that we've kind of learned in this process is just how quickly you need to start on this if you wanted to get to Pluto anytime soon. So to conclude, we've closed. This is a CML level 4, which I'm really pleased about. That was looking like it might not happen at the beginning of this process, but we've managed to do that. On a spacecraft and tour design that would visit 8 KBOs, so 6 in the Pluto system, a pre-Pluto KBO with the option of an extended mission to visit 1 more. This would get phenomenal, unprecedented KBO science. It really is quite difficult to do KBO science from the Earth. As New Horizons shown, in situ observations of Kuiper objects can revolutionize our understanding of them. And so we have 3 level 1 science questions that we think this tour would be able to fully answer, and an additional level 2 science questions that I've already talked to. We have 11 instruments. And like some of the other PMCSs have got to, our costs are still being worked, but it's looking like order of magnitude, it will be about $3 billion in FY25, and that's excluding launch vehicle costs. So this is very squarely in the flagship class. And the extended mission is coming out at just shy of $240,000 when that's added on. But of course, these are still subject to change as this is being worked. And so with that, I'm happy to take questions.
All right, so we have a number of questions in the Google Docs. If you haven't entered questions there, please feel free to. Some of these have been answered by Stuart Robbins. Let me ask one here. For mapping the dark winter hemispheres of Pluto and Charon, wouldn't synthetic aperture radar be the most reliable technique? The surfaces of Pluto and Charon could be mapped using SAR and the winter hemispheres compared with the illuminated hemispheres to see what terrains are shared and what are unique.
Yeah, we thought about that. We do have we thought about, we've got a radar included. It's not quite the same as what's being described. We kind of iterated on what we thought we should be carrying. Radar's expensive in numerous ways, and so we think we're going to get the best science for what the payload that we put together. But of course, other people might conclude differently should this ever be properly proposed. So I agree, you'd get great science with SAR.
Next question is, this sounds like it would produce a huge amount of data. Will there be enough time to get it all down between orbits?
So as you could see, I did show it will produce a huge amount of data. We can store, of course, some of that on board. We were trying to be data volume neutral. So the idea being that you could only take data in an orbit that you downlink in an orbit. So you're not holding a lot of it on board. Of course, in the real world, what you could do if you were going to do an extended mission is to take a lot more data and then slowly, as you fly to your next KBO, continue to downlink that data. I did show that it can fit in the box. Mark Perry at APL did a lot of work looking at typical data volumes and whether we could get all the data down that would produce our level 1 science, and showed that you could. And so lots of those times, in lots of the orbits, we're actually spending quite a lot of time away from the targets, and for most of that time, we'd be downlinking data. And so, you know, of course, the more data volume you have, the more science you can do. But as the technology has been improved, and I'm sure that'll only continue, we think it's going to be a bit quicker than New Horizons was to enable to downlink the data. So there's different ways of getting the data on the ground. But for sure, I mean, we could take a lot more data than we've proposed.
Next question is 5 RTGs sounds like a non-starter giving current plutonium production curves, even if no other mission requires the use of RTGs. How do you get around that?
It's a difficult one. Like I said, this was a big trade space for us. So we started out wanting to fit in 3 or less RTGs. The trouble is this is such a long mission some of the instruments are power heavy, and so in order to get the data down, you need power. In order to power the instruments, you need power. And so with the drop off in RTG power production, that was the number that we kind of settled on. If we did put in a caveat, and we do think there's a caveat whereby there are new power options that are coming online. Of course, nuclear power, fission power is something that's been talked a little bit about. And that would be an absolute game changer for this. So we agree 5 is a huge number, but this mission could probably be done on 4. 3 would be difficult, is what we found.
Thank you. Next question. Pluto seems to have a lot of challenges. Did you consider visiting another large KBO plus tour? And I think that means an orbital tour of another KBO.
We did. In the initial proposal, one of the ideas was to do a Pluto system tour and then onto another dwarf planet. And the Pluto system is it's interesting because it's one of the most diverse in that you have 6 targets, in one system. And so we think bang for the buck, you get a lot out of the Pluto system. There's still a lot of questions to be answered. Of course, another Kuiper Belt Explorer mission might conclude differently, but we thought the Pluto system gave good value for money in terms of the science you would get.
Next question, are there any special considerations that need to be taken for the long time horizon, related especially to DSN capabilities or any Earth-side resources?
So, of course, the mission design had to include a lot more redundancies because it is a really long duration mission, so extra reaction wells, those sorts of things. And so that all adds to the mass that you've got to fly. The design principles only use the 30-meter for downlinking the data. So having access to the 70 meters would, of course, be absolutely phenomenal in terms of the way in which you could downlink the data. So I think just making sure that we keep resources on the ground open, especially if we can access the big antennas, that's going to be really crucial for outer solar system science. So that's definitely going to be one of our recommendations.
Speaking of that, there's a related question. Did you consider optical communications to return the data with a smaller commitment of ground-based systems?
We didn't, not extensively. We decided, we sort of stuck to the decadal guidelines on this, in that we're just using the 30 meters, the 30-meter DSNs. Of course, again, any future mission could potentially explore those a little bit more than we have.
Looks like we have time for 1 or 2 more questions. What season will it be with regard to imaging the entire planet in sunlight, especially in comparison to New Horizons?
So basically the subsolar latitude has kind of gone up and then back down again. So I guess it's what would be half a season later. So the subsolar point is quite similar, but we're slightly shifted. So it's a little different, but it means that the surface that are in sunlight are pretty comparable to when New Horizons flew by it, for good or for ill. For good in that you can look for seasonal changes in those sunlit hemispheres, but for ill because the dark regions are still dark, and so Pluto moves slowly. It is what it is.
Let's did you consider using more than one orbiter?
No, we didn't. It would complicate things a lot, and we already felt like it was pretty complicated to get something there. So that would add, of course, to your dry mass, and it would delay your arrival time, which of course is going to reduce the power the RTGs have. So that's a trade that someone else might decide differently, but we wanted to keep it as simple as possible, even though it's still quite complicated.
All right. One question, maybe there's the extended mission cost, is that a 237K or is that a 237 million?
It's actually, it's a bargain. It's two, right now it's coming out at less than $300,000. Yeah.
Okay, that's in actual dollars. That's correct. Not a typo. Thank you.
That's not a typo.
Okay, one more question. Would waiting for kilowatt level enriched uranium reactor be more mission enabling?
Yes, it would. And basically anything that can increase the power to the EP system, especially if it's lower risk, at lower mass, would be really enabling. So this mission is really, power limited and mass limited are big things. We need to fly enough power so that we can get there in a timely manner. So anything that can be done to improve RTGs would help.